Welcome to the lesson on sensor types. Upon completion of this lesson, learners will be able to describe the 6 main types of sensors used in industrial robots and their characteristics, list the basic applications of each type of sensor, and recognize the various sensors used in industrial robots for EV manufacturing. Selecting the appropriate sensor for robotic applications requires careful consideration of several key factors. The choice primarily depends on what needs to be measured, the required level of accuracy, and the environmental conditions in which the sensor will operate. Robotic systems typically employ a diverse array of sensors to interact with and understand their surroundings. Some of the commonly used sensors are light, vision, sound, temperature, proximity, and tactile. Let's discuss these sensors in detail. Let's begin by discussing light sensors. As with many sensors, the name often provides a good indication of their function and the measured quantity. Light sensors are devices that measure some form of light or electromagnetic radiation. The electromagnetic spectrum, as shown in the right portion of the image, encompasses a wide range of wavelengths, from radio waves to gamma rays. Visible light occupies a small portion of this spectrum, shown as the rainbow band in the diagram, with other important regions including infrared and ultraviolet. Light sensors can be designed to detect various types of electromagnetic radiation within specific bands of this spectrum, providing information about the presence, absence, or intensity of light at particular wavelengths. One specific example of where light sensors are used is in light curtains, which are photoelectric devices designed specifically for safety and detection purposes in industrial settings. A light curtain creates an invisible barrier by projecting multiple light beams between a transmitter and receiver unit. When any of these beams are interrupted, such as by a worker entering the protected area, the system immediately sends a signal that can trigger safety responses like stopping nearby machinery. Light curtains are particularly crucial in manufacturing environments, being commonly deployed around robotic welding stations and assembly areas where they act as a critical safety system. While these devices can be configured with visible alignment LEDs for setup purposes, they typically operate using infrared light, making the protective barrier invisible yet highly effective. This invisible operation ensures the light curtain doesn't interfere with other operations while maintaining robust detection capabilities. This image shows a robotic work cell protected by light curtain sensors, highlighted in red circles, that create invisible safety barriers around the perimeter, with an enlarged detail view of a single light curtain sensor unit shown on the left. Like light sensors, vision sensors measure something visible to humans. The most common term for a vision sensor is a camera. Vision sensors combine cameras with image processing capabilities to capture, analyze, and make decisions in real time. These devices use cameras to identify shapes and outlines within their environment, while their integrated computer processing systems triangulate exact dimensions based on the captured images. Vision sensors serve multiple industrial applications. They sort objects based on size, shape, and color, making them useful for quality control and material handling. In robotics, vision sensors help with path planning by providing spatial data that robots use to navigate their surroundings. They also enable obstacle detection and avoidance, allowing robots to operate safely in changing environments where they need to identify and respond to objects in their path. Next, we have sound sensors, devices that detect acoustic waves and convert them to electrical signals. These sensors measure, monitor, and respond to various sound levels and frequencies, including those beyond human hearing range. The operation of sound sensors relies on the piezoelectric effect, where specialized materials generate electrical current when they experience mechanical vibration. Microphones are a common example of this principle in action. One important application of sound sensors is distance measurement, where they emit and receive ultrasonic waves similar to radar technology. Sound sensors find applications in both consumer and industrial settings. In consumer applications, they enable voice-controlled home automation systems like Alexa, where they capture and process voice commands. In industrial applications, sound sensors are fundamental to radar and sonar systems, which use sound wave reflection for navigation and object detection. In manufacturing environments, sound sensors integrated into robotic systems monitor equipment vibrations and unusual noises during operations, helping detect potential mechanical issues before they lead to failures. The next type of sensor is the temperature sensor. These are devices designed to detect and measure heat energy present in objects or environments, converting thermal energy into electrical signals that can be processed and monitored. In industrial robotics and manufacturing, temperature sensors play an essential role in welding operations, where they monitor and control heat levels to ensure proper weld formation and prevent material damage. They also enable automated sorting systems to handle materials based on their temperature characteristics, which is particularly useful in processes where thermal properties affect material handling requirements. For example, in foundries or metal processing facilities, robots equipped with temperature sensors can determine if materials have cooled sufficiently for safe handling or if they require additional cooling time before further processing. These sensors come in two main categories: thermistors and thermocouples, each offering different advantages for specific applications. A thermistor is essentially a temperature-sensitive resistor that exhibits changes in its electrical resistance as temperature varies. It utilizes metal oxides with different temperature coefficients and requires an external power source to function. The thermistor can be seen in the image, where it appears as a small component on a circuit board designed for temperature sensing. In contrast, a thermocouple consists of two different metal wires joined at one end to create a measuring junction. When this junction is exposed to heat while the other end, known as the reference junction, remains at a known temperature, the thermocouple generates a voltage that varies with temperature. Unlike thermistors, thermocouples produce their own electrical energy and don't need an external power source. This voltage can be measured using a voltmeter, as shown in the diagram, providing an accurate temperature reading based on the temperature difference between the hot and cold junctions. Next, we have proximity sensors, which are devices that detect nearby objects without requiring physical contact. These sensors operate by emitting signals, either electromagnetic fields, light beams, or sound waves, and then measuring changes in the return signals when objects enter their detection range. Proximity sensors come in three main types, each suited for different applications. They are inductive, capacitive, and photoelectric proximity sensors. As mentioned previously, proximity sensors come in three distinct types, each designed to detect objects using different physical principles. Inductive proximity sensors, shown in the image with a blue cap, create and monitor electromagnetic fields to detect metallic objects, making them ideal for applications like metal detection, speed sensing, and position monitoring in manufacturing environments. Capacitive proximity sensors, seen in the image with a yellow cap, generate an electrostatic field and detect changes in capacitance, allowing them to sense a wide range of materials including metals, plastics, liquids, wood, and glass. These sensors excel in level sensing and material detection applications where versatility is needed. Photoelectric proximity sensors, seen in the image with a distinctive red light emitter, operate by emitting a light beam and detecting either reflected or interrupted light. They can detect most materials except transparent objects, making them well suited for object detection, counting, and precise positioning tasks in automated systems. Each type of sensor serves specific roles in industrial automation, with their selection depending on the target material and application requirements. So, starting off, we have an inductive proximity sensor, which we talked about is good for gauging distance. So, as material comes up to it, flux lines change and the inductance changes. For capacitive sensors, because we can get information from changes in dielectric, we can use them to judge whether material is exactly as we expect or not, causing some rejection for bad materials. And then lastly, we have a photoelectric proximity sensor, which is basically a break beam light. It could correspond to our light sensors that we've talked about before. An example that we can all relate to is a garage door opener. If you walk through the garage as it is closing, the sensor triggers the door to stop as a safety feature. Finally, let's discuss tactile sensors. These are devices that measure and respond to physical contact or touch. These sensors convert mechanical force, pressure, or deformation into electrical signals that robots can interpret. Tactile sensors enable robots to detect when they make contact with objects in their environment, and they can measure the amount of force or torque being exerted by the robot's end effector during interactions. This functionality mimics the human body's process of sensing, similar to how we push on something and feel its resistance. In robotic applications, this ability makes them suitable for tasks like grasping and manipulation. In electric vehicle production, various sensors integrated into robots play specialized roles across different manufacturing processes. Some of the applications listed here demonstrate how different sensor types could work together in EV manufacturing to maintain quality throughout the production process. Light sensors are employed to ensure proper chassis frame alignment, while vision sensors handle the inspection of door panel fit and finish quality. Sound sensors serve purposes such as conducting ultrasonic weld inspections or performing acoustic testing of motor bearings. Temperature sensors monitor spot welding processes in the body shop to maintain optimal welding conditions. Proximity sensors assist in precise robot arm positioning during dashboard and seat mounting operations. Tactile sensors control the force applied during glass windshield installation to ensure proper mounting without damage. In summary, the selection of sensors in robotics is driven by three key factors: the specific quantity that needs to be measured, the required sensitivity and accuracy of measurements, and the conditions of the working environment. These sensors function by converting physical signals into electrical voltage or current that can be processed by control systems. The various types of sensors include light, vision, sound, temperature, proximity, and tactile sensors, each serving specific purposes in robotic applications. Whether working independently or in conjunction with each other, these sensors ensure precise operations and quality in EV manufacturing processes, from chassis alignment checks to windshield installation. Thank you.